Yeah, so we are the last chapter of this book. Yep, so maybe I'll just get started. So in this chapter, the author covered 5 topics. He talked about how to serve models with TensorFlow serving, how to deploy this model on Google Cloud, how to deploy a TensorFlow model on embedded devices, how to deploy a TensorFlow model on the browser with TensorFlow.js, and finally, how to train a model on multiple GPUs and TPUs. So let's get started on the first topic, TensorFlow serving. So what is TensorFlow serving? Yeah, so TensorFlow serving is a web server from Google. It can serve TensorFlow models. One nice thing is it supports serving multiple models at the same time in one server. And a model can have different versions. So it will allow, like, if a new version is added, it will automatically serve and deploy that version. One nice thing is you can have in one TensorFlow serving web server, let's say, you can serve one model with a CPU, one model with a GPU. Some other nice things that it has is, if your server is maybe getting like 100 requests per second, you can tell TensorFlow to automatically batch those requests, either with like a time constraint or like, if you get 32 requests that are coming at a certain millisecond, to kind of treat them as one request and send it to the GPU. So it's more efficient in using the GPU. And also, like, from a production kind of mindset, it also exports like metrics with Prometheus. So like in a large organization, there may be like Grafana dashboards that are like monitoring the latency, GPU usage. So it kind of supports all these things built in. It's easy to, like, once you have your Keras model, you can just call TensorFlow.savedModel.save, and it will export your model to a saved model format. This is basically what would be in the directory. This is the version that you created, the variables in the TensorFlow graph, the protobuf file that contains model. Yep, so a little bit more detail on what a saved model is. So a saved model, there's a CLI in the TensorFlow serving SDK. If you run it, it shows you this graph. It shows you this metagraph. So a saved model format can have one or more metagraphs. And a metagraph is just a computation graph with like signature definitions. So here you see the signature definition. It tells you what the inputs are, what the outputs are, what the shapes are. Technically, a metagraph, like a saved model, can have multiple metagraph definitions. So you might have like your original graph, TensorFlow graph for your original model that you had for training, like without any optimizations applied. But at serving time, you might have a more optimized version of your TensorFlow model where, any operations that could be combined together could be saved. But by default, when you call like TensorFlow.savedModel, it'll only save one metagraph with the signature definition of serving default. Sorry, that was a lot, but if to make things simpler, just assume that if you call TensorFlow .saved model, you'll get a saved model that you can use to serve. Yeah, so this is basically kind of what we mentioned about, and Google has some nice TensorFlow serving Docker containers. So you can use the default TensorFlow serving image from Docker Hub. You can mount the volume that you have your model into the volume that the container is expecting. And after a couple of seconds, then you will have a gRPC endpoint and an HTTP endpoint that you can hit to get requests for your model. So if you want to make a request to the HTTP endpoint. You just JSON serialize your request. So this is the signature definition that you want to hit. Instances is the request that you want to send. And if you look at the server URL, you have like v1/models. And again, as we mentioned, we can have multiple models that we can serve. But here we only have one model, and yeah, we just make a post request. So this is basically how to use TensorFlow serving. But before, I just want to give maybe some reasons why TensorFlow serving may not be the right choice. So, in your company, if you only have one model, or you have a practice of serving one model per container, like the whole TensorFlow serving of looking at a model registry or a model store may not be the right pattern for you. If you're only doing CPU-based inference, then I think using like Flask or Fast API might be fine. And then like if you're using like TensorFlow eager models, or there's some dynamic part in your graph, or if you have like custom pre-processing or post-processing that you need to do on the input or the output of your model, like TensorFlow serving doesn't really support those use cases very well. So these might be some reasons why you may not want to use it. Yeah, so that's all the information I wanted to share on TensorFlow serving. Like before I go to the next section, were there any questions to go over? Or
I really like this slide. I think the book didn't make it as clear, like why you might not choose this. And so I don't think most things that people do don't tend to have dynamic models. But if you have an if statement anywhere in your neural network model, then that makes it dynamic. You can sometimes rewrite an if by turning it into a max or something like that. But if you see, the keyword if, then you're definitely up the creek. And then also, if you make calls out to generic Python libraries. So the book has talked about how you can sometimes wrap them and get them converted to TensorFlow functions. But if you're not able to, and it's calling out to some other library that's Python or C++ or whatever, then you're up the creek, because it won't be able to create that TensorFlow static computation graph from that. And so I think then it's not even, it may not be right. It just flat out won't work.
On that point, I know this is the whole TensorFlow piece, but like if people have worked with the PyTorch side, I think PyTorch has TorchServe, which I feel is more flexible with some of these things. So it has hooks that you can easily do like pre-processing, post-processing, or inference. So I feel like the design for that is a little bit better. But yeah. Cool. So let's go to the next section. This is a little bit short. So maybe you're a small developer or a small team, and you want to deploy it to the cloud, and you kind of don't want to deal with scaling. So let's say you decide to go with Google Cloud. So the first thing, we saw that folder that contained our model. So just create a Google Cloud storage bucket. Upload those artifacts from after we call TensorFlow.save. Then Google has a managed offering called Vertex AI or AI platform that you can basically point it to the GCS bucket, tell it to enable logging, tell it to enable auto scaling, tell it to specify the machine type, GPU type, and then it will just serve it automatically. Yeah, and if you don't want to expose your model publicly, and all your resident clients are inside your cloud environment, you can use the Google Cloud API to basically deal with the authentication. Yeah, so just create a client ML resource with using this automatic client discovery. Here you notice this is the same format we created to create a payload, but instead of using request.post, we're using that client that we created called predict. Other than that, it's basically same, but it's all secure inside Google's cloud environment, so you don't have to expose it to the outside environment. Yeah, so that's basically all I had about Google Cloud Platform. Yeah, so the next section, which is kind of interesting, is you have your TensorFlow model, and now you want to deploy it to either an edge device or your mobile phone or whatnot. So TensorFlow Lite was this again, a library from Google, which makes the process of taking your TensorFlow model and optimizing it for mobile microcontrollers or other edge devices. And when we train like on our desktop or on our servers, we have these large model files, 100 megabytes or so, and that's a little bit too big for our mobile phone or even smaller devices. So you definitely want to see how you can reduce the size of the model, reduce any computations that are needed, because the computation processor or the CPU for these devices is even slower. And also things like battery usage and heating becomes more important for these devices. Luckily, converting to a TensorFlow Lite model is very nice. So once you install TensorFlow Lite, you can just call tf.lite and give it the directory of your saved model, and you just call convert, and it will create this file for you. Some of the optimizations that TensorFlow Lite does. So by default, when you use like TensorFlow saved model, it uses this. It uses protobufs that are not like that are not easier to load in memory. So when you use like flat buffers, as long as you load the asset, it directly maps to memory. So you don't need to do any like pre-processing or mapping. So it's much faster to read in memory. Another optimization that TensorFlow Lite allows you to do is pruning any operations in the graph that might not be needed for inference. And some other small things that it could do is like if you have multiple layers, it can fuse the layers. So the example in the book is if you had like 3 times a plus 4 times a, you can just do this addition once and do a multiplication once instead of doing this frequent multiplications. And then the book talks about another optimization, post-training quantization. So what exactly is post-training quantization? The basic idea is, when we train our model, we might be training our model with like 32-bit precision, but maybe when we are doing inference, like, do we really need that level of precision? Can we map from like 32-bit floats to 16-bit floats or to even like int 8? So if you have a mapping from -1.5 to plus 1.5, you can create a mapping to like ints from -127 to 127. So you're reducing the precision, but from 32 bits to 8 bits. So obviously you will get some accuracy difference, but hopefully it wouldn't be too much. Yeah, so if you're going from 32-bit precision to 16-bit precision, you're basically reducing the weights by half. So the model storage would be half, and it'll also load in memory a bit faster. And one thing to mention, like the technique that we just talked about, it's not really like what's happening is the model weights are saved with let's say 16-bit 16-bit floats or int 8, but at runtime when the computation is happening, it maps the 16-bit floats to 32-bit floats. So what you're actually saving here is the storage or like the memory that you are loading the model, but like when the computation is actually done, it's actually doing it in the original 32-bit floats. Yeah. There are other quantization techniques where you're actually quantizing the activations, but this is a pretty simple quantization technique. So this is from the TensorFlow documentation, just to show like if you did this post-training quantization, what is the accuracy drop that you might see? So maybe if we take a look at this MobileNet v2 model, the top one accuracy for the original 32-bit model is like 71%, 71.8%. But if you do 16-bit quantization, it drops a bit to 71.3, and if you do int8, it's 71.2, which it might depend. I mean, these seem like very, very small drops. Yeah, so I can only really speak for MobileNet and MobileBert. So here for MobileBert, like we see like for int8 activations, it's just not enough to capture the information at all. I mean, there's a very, very wide drop, but 16-bit quantizations seems to work for most cases. Yeah. So yep. So another thing, just to show like our iPhones or our mobile phones, like the Google phones, like they have specialized accelerators. And if you use TensorFlow Lite, you can help kind of use like if you use the Android SDK for TensorFlow Lite, or if you use the iOS SDK for TensorFlow Lite, you can kind of get some good results. So if you look at, let's take the Google Pixel 4a. So if you use the 32-bit float model for MobileNet, it takes about 63 milliseconds inference. But if you use the quantized model, it takes 30 milliseconds. And then if you use TensorFlow Lite and use the specialized accelerator that's available, like for 16-bit floats, it takes 21 milliseconds. And for int8 models, if it makes sense, it goes to 8 milliseconds. And if you look at the more recent specs for the Pixel 6, the CPU time is about the same, like 64 milliseconds. But if you use the neural net API to use the accelerator, you're getting all the way down to 2 milliseconds and 1 millisecond, which seems really amazing for a MobileNet model to run. Yep, so I went a little bit fast. Did this make sense? Yes, sorry. This is the same number. Yeah, so if you, there's this website where I pull the numbers. They actually have an Android app where you can download and get the benchmarks on your own phone for MobileNet, object detection, and other types of models. So you can actually see how long it takes. And you can also customize like whether to use just CPU-based acceleration or to use the neural net acceleration. And it's pretty detailed benchmarks it gives. Yeah, so that's basically what I had for deploying on embedded devices on mobile using TensorFlow Lite. Cool. Yeah, so the next deployment option, deploying on your browser or in a JavaScript environment using TensorFlow.js. So, like if you wanted to, like we all use Python, but I would argue like maybe one of the more popular programming languages is JavaScript. So, if you want to deploy your machine learning models in a JavaScript environment, like the browser, or even on the server, like a Node.js environment, you probably want to use JavaScript. But other reasons why you might want to use like a deployment environment, like the browser, or like a browser running on the user's phone, like if the user has like bad internet connection, you probably want the model to be running on the user's phone. You probably don't want the user to upload like an image or everything like to the server. Like if everything can run on the browser itself, like that would be great. Depending on the use case, you might actually get faster inference because you're not sending the data or the payload to a server. You're actually doing inference on the browser itself. And that gives like some privacy benefits also. Yeah, so I have a small demo just to kind of show what you can do with so here's the MobileNet model that 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 was trained like on this Food 101 data set. And like on the left-hand side, I have the browser making a request to a Flask service that is hosting the TensorFlow model. And then on the right side, I have another option where the browser is going to do inference locally itself with TensorFlow.js. So, we see about the same results. So on the server, it actually took a little bit. It took a little bit of time for my browser to send it. I'm running on Heroku free tier, so the server may not really be up all the time. But it took like close to a second for the complete round request. And on the browser, it took 84 milliseconds, like running on my machine. Let's see if it can run a little bit. Yeah, so the first time that TensorFlow.js run, like it doesn't load the model completely in memory. It only does it once the first computation happens. But the second time, since the TensorFlow.js model is already loaded in the browser, like it doesn't need to load the model. It just can do the computation. So this is MobileNet, and this is a small model. Obviously, there's some latency gaps that are happening here, but you can see that this is a pretty good inference time. Cool. So let's see. Sorry. So they're also pretty nice examples. So again, once you can, this is a Python module, TensorFlow.js converter, that can export the model to the TensorFlow.js format. And then, in JavaScript, whether it's in the browser or on Node.js, this is basically how you will load the model and make a prediction. And I just kind of want to show like some other examples that, the interactivity that you can have with using the browser. So there's a pretty nice community made with TensorFlow.js that kind of shows some of the demos. So this is a demo I kind of like, where this person shows how you can use the browser to basically create like a Sudoku solver, and then you kind of use AR to kind of place a solution. So the browser, you're pointing, giving it camera permission, it takes, or you upload a picture of the unsolved Sudoku game, using some object detection to find the connected components, and then you have a simple digit classifier to kind of recognize the digits, and then you use like just AR to kind of place the images, place the solution on the thing. So it's a pretty simple example, but I think it was pretty cool. Another one that I really liked was this yoga.ai. So basically, this person created this thing where in the browser, it runs like the postnet model to identify like the poses that you're using. And then this person trained a simple classifier to kind of recognize the poses. And you can kind of see like, if you have your browser or you're pointing the camera to, you can basically see, it can give you feedback on how you're doing certain yoga poses or whatnot. This is all running on the browser, no data being sent to the server. Pretty nice examples. Sorry. Yeah, so that's basically what I had on TensorFlow.js. The final section is on this, but before I go there, are there any questions?
So I just had a thought when I was reading about this, that theoretically, if you do TensorFlow.js, well, one thing is just that you compared sort of the inference time, but the page load might be longer because it's downloading the whole model versus if it's server side, it's not, right?
Yes.
But then I did also have this thought that theoretically, since somebody now has access to your whole model, then they can see all the weights. So if there's a bad actor, they could do adversarial analysis of your model if they wanted to. So this wouldn't be good for like a secure kind of a application, right?
Yep, those are good points. Yeah, so I didn't really mention this. Like, I think one of the problems I still feel with TensorFlow JS is like, even if you make the model size small and like it's like 4 megs or 5 megs, like that is still a little bit too much. I mean, like, companies and whatnot, they think of apps or websites, trying to reduce the payloads to under 2 megs or something for like the initial load time. But here, unfortunately, the models are still pretty large. And also the other point, exactly as you mentioned, like, I mean, these models are like, unless they're not sensitive or good for demo purpose only, would you really would any company be comfortable sending their completely sensitive model running on the device or on the browser that anyone can just download? So since it's running on the browser, you can see like the network call that's made, and you can also download the model for your use case offline. So yeah, those are definitely some good points to consider.
Yeah, like if this were a business thing, your competitor could just copy all your weights.
Yep. Yeah, but it is cool, some of the demos, definitely. But yeah, definitely the business side. Yeah. Cool. Yeah. So here's the final section. Sorry, this is a little bit different from all the things we talked about deployment, but not training. So, if you're lucky to have an environment where you have multiple GPU devices, you can use the environment variables like CUDA visible devices to kind of limit what GPUs are available to different Python processes that you might spawn. So you can have one process that sees GPU 1 and 0, and another Python process that only sees GPU device 2 and 3. The book talks about two models for two types of parallelism. One is data parallelism, and the first one is model parallelism, and the second one is data parallelism. So model parallelism is you basically split the model across multiple devices. So here's an image from the book. If you have a CNN on the left, one thing you could do is maybe you can split, if you have 4 GPUs, each GPU has one layer. Unfortunately, that doesn't really work that well because there's a lot of network traffic that needs to happen for sending the information. Another thing that you could probably do, depending on the model, is maybe you could split the model vertically, and half the layer computation is happening on one GPU. I don't really see model parallelism really used anywhere unless maybe for some special models. So as the second pattern I've seen used a lot more, which is data parallelism. The basic idea is you basically replicate the model on each device. You run the training step on each of your device using a different mini batch. And then you basically accumulate the gradients and you average it and then send it to all the replicas, and they update they update their own models. Yeah. So here's an image for data parallelism, just showing the same thing. All the GPUs, whether they're on the same device or on different machines, they have the model loaded, they do the computation, they have this shared step that they may wait for, that they all have to wait for, where they accumulate the gradients, and then they each update. So this is a step that could be slow, the mean cooperative operation, but every other step could happen independently. So in this example here, like all the workers have a GPU attached, but depending on the use case, you might actually want to have this parameters kind of be stored on a separate worker, maybe just a CPU worker that doesn't actually do that doesn't actually participate in the model training. So this is called a parameter server. So you have a specific machine, like a CPU machine that just hosts and update the parameters. And kind of one other thing you can do is, if you are training maybe with 4 GPUs and, for whatever reason on one of the GPUs, like the training, it's taking a little bit more time to train for an epoch, what you can do is basically say, hey, at least have the gradient information from 3 GPUs. So I'm going to ignore the 4th GPU. Yeah, so this is same thing, just with a different worker. The book shares these numbers. So if you look at a mobile, if you look at the image model like Inception, on the ImageNet data, like on 50 GPUs, you're apparently getting like 32x speed up. On a translation model, you're getting 6x speed up. So you're not always getting like the linear speed up that you might expect. So there's definitely the cost of the network communication of sending all these weights, but definitely it's much faster than just using one GPU. And the TensorFlow library does a pretty good job of making all these things simple. So if you use the strategy of using all the GPUs on one device, you can use the strategy called mirrored strategy. And you just, with this decorator, you wrap your model, and then you just call like model.fit. And the only thing you need to take care of is you need to take care of a larger batch size that's divisible by the number of GPUs that you have. And then the TensorFlow library will take care of all the creating all the replicas and then accumulating all the gradients and all that. The other thing is, if you want to use a different parameter server, you can use this different strategy called central storage strategy, but then otherwise all the things are the same. If you want to use a TensorFlow cluster, where you actually have workers on different machines, you can create this cluster spec where you have the workers and parameter servers specified. Then you create an environment variable where you're saving these things. And then again, the same thing, you just change the distribution strategy and TensorFlow automatically will take care of this. So before we had like a mirrored strategy, here we have a multi-worker mirrored strategy. Maybe in the future, it might be combined, but for now. And again, TensorFlow makes it a little bit simpler to use TPUs. I personally haven't used TPUs, but assuming you have the environment variable set, if you just use this resolver, and then you have a client that you can kind of use the same setup that you saw in the previous things. And like maybe you don't want to deal with managing the GPUs like all the time, because you might keep it idle and cost concerns or whatnot. So Google Cloud has kind of a way to submit a batch training job where you can specify the your source code where it'll download. You can specify there be scale tiers where it specifies the machine specs, the GPU specs, and you can just tell it to like, hey, here's my model, do the training, save the trained model elsewhere, and it'll then tear down all the infrastructure afterwards. So I believe this is all I had for the chapter. Sorry, there was 5 different areas, but it was, all things considered, it was like a little bit succinct. But yeah, that's all I had. Any questions?
Very cool. Yeah, that was well organized. That was very clear. I don't think I have too much to add. Ryan, anything you would add just from having actually tried to use multiple GPUs or anything like that?
Nothing really to add. This is what I've been kind of fighting recently, and I have to say a lot of these tools are not fun to work with. Lots of things that seem kind of half-baked, but that's all I can really add. Is this stuff is very important to actually get the throughput and the models deployed, but it's not easy to do.
Yeah, and I think I would assume it's probably true that even if you're fortunate enough to have 4, 8, however many GPUs, and they're all identical, they're all the same, model GPU, they're not all necessarily going to return at roughly the same time. There could be communication of the inputs is faster or slower to one or the other. And then also my understanding is just like if some of them get hotter, they're going to run slower. You know, once they've warmed up, once they get hot, then they're actually going to get throttled, and so they're just not going to have as many, you know, flops as the other ones. And so you'll just notice that this one that's really hot is like, say, you know, 10% slower. And so what you said before about, you know, instead of waiting for every single last GPU to finish, you might just say, I'm going to wait for, you know, all but the last one or two. And then when I have that many, that's close enough to do an approximate gradient. I'll just average those up and ignore the last ones.
One question I have for the group is like, you know, if you have used the PyTorch side of things, like, do you feel like the PyTorch multiple GPUs and either with using PyTorch Lightning or just the original raw PyTorch, like, is the APIs cleaner to use for multiple GPUs or TPUs or whatnot, or do you experience with those?
I've been working with PyTorch stuff right now. That's what I've been working on. And it doesn't seem much better in my opinion. It depends on the models. Like there's certain trivial cases where it's like, okay, you just plug this in and then it works. I've been working with some models that are a bit more involved and they can't parallelize as easily for various reasons. So like in my case, they return a dictionary rather than just a matrix, because the matrix, it's easy. You can just concatenate them back together at the end. But the dictionaries, it makes everything completely different. And you would think that would be something somewhat simple, but in reality, you either have to change the model or you have to do a whole bunch of legwork behind the scenes. So that's what I've been running into, is I don't feel like it's completely there, but I'm sure in some trivial case it works perfectly.
Cool. Yeah, thanks for sharing.
Hey, Ryan, do you know, so like ideally someday PyTorch Lightning might become like Keras, where it simplifies things and, you know, you don't have to specify the size of the inputs on every layer. It just calculates it for you. But Keras doesn't really do the distributed stuff. You really have to do it at the TensorFlow level. And I don't think PyTorch Lightning has distributed functionality, distributed hooks. Do you know?
PyTorch Lightning's main function is all of that stuff, actually. It's giving you the infrastructure piece. It doesn't do nearly as much on the Keras side where it like helps you build the model. It tells you basically define your model in various different ways with these different classes and functions and etc. And then it hooks into the PyTorch Lightning kind of ecosystem, and it helps you do that distributed training and logging and all of that stuff. It helps you do what's it called? The mixed precision and all of that stuff. I've been looking at it a lot because I was trying to figure out how do we split this work across multiple GPUs, and that's one of the things where in our scenario we're using this model that has already been completed, and so kind of saying let's make this fit in PyTorch Lightning, it doesn't really make sense because they're saying just redo the model and do it in our format, and it's like, well, I can't. But yeah, PyTorch Lightning does multi-GPU, multi-system, all of that stuff.
Okay, so definitely an option for people to look into. Yeah. Okay. Since we have the time, I think I would mention, so in the earlier topics in terms of like mobile edge, in the book, you know, we talked about some things to make the model smaller, and then even talked a little bit about you can reduce the data types in your model when you're training it, which of course potentially introduces, you know, some errors. So I don't think the book necessarily touched on it, but I think now we can say that there's quite a bit of support in both TensorFlow and PyTorch for this mixed precision, half precision floats. And so I think to a large extent, and there's also, NVIDIA has a whole bunch of mixed precision optimizations built into their latest generation of GPUs. So you can get significant training speed up if you use mixed precision. I don't know a ton of the details, but I know that there's support in both TensorFlow and PyTorch. So that's something that you can look at. But then as you go more towards mobile and edge, then you get into, it's sort of more work, because mixed precision, you can practically do just a handful of lines of code and just change your model to use mixed precision. So there people will actually run their models at a much lower precision, and the book mentions, but just very lightly, so I think I'll go a little deeper, right? You can after the fact change your model, but then potentially, like you saw for that mini BERT, when they went to 8-bit, it just was catastrophic. It went from, whatever, 80% to 2% accuracy. It just completely. But if you train at that lower precision, then that means that your weights and the whole model is used to that lower level of precision. So it may never get as high as the original full float, but then it won't be catastrophic. And so basically what happens then is there's a lot of rounding that happens because you don't have as much precision, but that rounding, the model's getting used to it the whole time it's training. So it's a little bit like if you think about dropout in a model, eventually the model gets used to the fact that this dropout is happening and it acts to regularize it. And so if you train at a lower precision, then the model, it treats that noise as sort of like a regularizer. And then definitely a topic that I don't know a lot about, but there are people who then do pruning of models after you've built them. And so it'll say, oh, well, here's a node that has, very, very few activations. We can just completely remove it from your model and the performance won't be that different. And I know there are actually some companies where what they advertise is that they have highly pruned, much smaller, faster models that you can use either just for faster serving or for things like, edge devices. So I've definitely seen, some of that. So there's, if this is an area of interest for you, then there's definitely more than what the book covered in terms of what people are trying to do to squeeze out smaller models and faster performance. I don't know, anything else anybody would add just in terms of your experiences or questions on this topic?
Ted, to kind of jump off where you stopped on the smaller models thing, there is this whole concept of TinyML, where you're running models on extremely small microcontrollers. By extremely small, I mean devices with like 64K of memory. That's the, the totality of the world, and you can still do machine learning on those. And when you go to those, you're typically a 8-bit integer world. So of course, your model is going to be 8-bit. And your processor, let's say, is lucky if it does not gigahertz, but maybe like 40 megahertz or something like that. So inference time and things like that. The good thing, of course, is that you can run these devices off a teeny weeny solar panel or watch battery or something like that for a month. So when you think about deploying them into maybe into a farmer's field or something like that to watch for harmful insects, and your vision model is determining between a harmful insect and a good insect, these things are really devices. And you're seeing a lot more push into the TinyML space. So this whole concept of quantization down to small models is becoming more of an issue.
And Jerry, with the reading that you've done, are people taking other models like a mobile net and just going crazy to make them smaller, or are they having to just start from something that's smaller to begin with?
Both.
Both? Okay.
Both. It depends on the problem they're trying to achieve, but both ways are possible. MobileNet, does a lot in a lot of the cases that I mentioned, mobile may actually be overkill for what you're, what you're trying to accomplish. With these small devices, if you think of an Alexa, for example, and doing wake word detection, oh crap, I just triggered my, sorry. One of the things is that those models are extremely tiny. I believe the one for, okay, Google, I hope I didn't trigger anybody's phone, is something like 6K or something like that to detect that word, and then turn the speaker on, then bring up the whole connection to translate what your next bit is going to go. And so when you get into that type of thing, then you're building a very, very customized model to shrink it down and not take up a lot of space. But, we're talking, this is a growing space because you're talking in terms of not millions of devices, but billions and tens of billions of devices. If you start thinking about, you're going to have your car lock or something like that, that's going to have that. So these are, large industrial scale type where your machine models will be deployed.
Cool. Thanks.
Yeah.
All right. Anybody else have a question or anything they want to add? Okay, cool. Well, nice job. Very clear, great organization, and thanks again for the extra benchmarks and other examples that you added in to the book topic. I thought that was really great. All right, well, so this is going to then wrap up the formal set of chapters for the hands-on machine learning book. We do have the graph machine learning series that's going on alternate weeks, although I will just mention administrative note, if you look on Meetup, you will see that normally every other week we'd have the graph machine learning, we'd have a session next week, but just due to scheduling conflicts, it's actually pushed out to the 30th. So next week, there will be no San Diego machine learning meetups. There won't be any book club or whatever at 12, and we're also not doing the 1:30 project discussion. So next week's just a week off, and then in 2 weeks, we'll be back talking about graph neural network augmentation training. And we haven't decided yet. I'm actually going to be polling the discussion leaders to see if they have a book or topic that they're interested in doing next, and we'll see if there's any kind of consensus or if it's a lot of different ideas or what. All right, so I think that wraps up today's session and wraps up the hands-on machine learning book. Ryan, we've got a little bit of time before the formal start of the project discussion. Do we want to fill, or maybe just give people a little bit time to grab a bite to eat, take a break, and then just reconvene in 20 minutes?
I think probably just take a break. We don't need to fill.
Yeah. Okay. All right. Thanks, everyone. So if you're going to stay with us, then we'll see you back in 20 minutes, and you can ask your project questions, coding questions, whatever. We can chit chat about just machine learning news. All right. Thanks, everyone.